Okay, thank you very much. So it is pity that I also could not join you today because of the family issues, not the pandemic reasons. But I will try to tell you about inclusion compounds, especially the clatrates, which can show both thermoelectric and also the superconducting properties. Yes, I am from Istanbul, from Koç University. Let me start with a brief introduction about the superconductors. So we have different kinds of superconductors, basically. This can be divided into several categories. So these are, let's say, like the metallic superconductors, as you can see here, copper-based superconductors, iron-based ones, magnesium diboride, and also the hydride superconductors. So we have thousands of these superconductors have been discovered, but the ones with practical value are limited only to the niobium titanium, niobium tin, copper-based superconductors, magnesium diboride, and also the iron-based superconductors. Very recently, this room temperature superconductivity was discovered for the hydride materials, but then these materials were showing this superconductivity near room temperature or little above room or close to room temperature under very high pressures, like 267 gigapascal, for example. So one of these material, for example, lanthanum H10, is called clatrate hydride. So it's another clatrate form, but in the hydride form, not intermetallic clatrate, but in the hydride form, and it shows also very high superconductivity. There is also the sodium version of this clatrate hydride, which is basically sodium H6. It shows TC of 180 K and at much lower pressures. When I say lower, it is still high, but let's say 50 gigapascal of pressure. Okay, so superconductors are used in many different applications. For example, in high efficiency electric power generation, high capacity lossless electric power transmission, small lightweight electrical equipments, in magnetic magnetic levitation transportations, in NMR, MRI, and so on. Okay, so thermoelectrics, I will discuss about that. The clatrates actually, they show the superconducting behavior, but also they are very promising thermoelectric materials. Now, our motivation in thermoelectric research is to actually harvest the waste heat, because here on the left side you can see the sources of the energy, and mostly still non-renewable energy sources. And out of this, let's say 100% energy, just a little above 30% is actually the useful one, and almost 2/3 of this energy is lost as a form of waste heat. So the thermoelectric materials, they can harvest this waste heat and convert it to the electricity, and at the same time, as the Professor Moya was explaining in the previous talk, they are also functional materials for cooling. So in our case, a small increase in thermal efficiency by this waste heat harvesting could make great impact in the energy sustainability, and it can help us to reduce also carbon emission, as was discussed previously. Okay, so thermoelectric materials have this solid state nature, and this basically provides no moving parts, no maintenance is needed. They have long and also predictable life, and they are scalable, so you can basically build different materials or like different systems from micro to meter scale. So the first talk was discussing about the applications of thermoelectric materials, so I will not take time. It was used basically in the spacecrafts actually for many years now. It can also be used in energy harvesting applications such as these automotive applications, and also the in medical sensors, smart watches, and etc., which basically uses body heat as the heat source and convert it to the electricity. So they are functional materials for cooling or thermal management applications. For example, for small refrigerators, which can be used in medical applications, in cooling the car seats, for example, or in optoelectronics or detectors, in which more precise cooling needed. So you basically tune this cooling by changing the current that I will explain you in a moment. Okay, so this is the thermoelectric theory. So we have both power generation and the cooling property. So in the power generation, what you do is in the circuit, you apply just a temperature gradient so that the charge carriers in the N-type semiconductors and P-type semiconductors, they move from hot side to the cold side, and this creates actually potential, and the potential amount of potential per temperature gradient is giving us the Seebeck coefficient. Now, if instead of applying temperature gradient, if you apply current here to the same system, then you force the charge carriers to move from one side to the other side, and this basically creates this cooling effect. Now, we define the thermoelectric efficiency with the thermoelectric figure of merit, and this is related to the Seebeck coefficient square times the electrical conductivity divided by the total thermal conductivity. So we want to have high voltage created per temperature gradient. We want to have high electrical conductivity, but at the same time, we want to have low thermal conductivity so that we can actually retain this temperature difference in this system. It is hard to make actually, hard to achieve this high ZT than for one material. In the device efficiency, the device efficiency is related to the Carnot efficiency times a function of this material ZT, but then instead of one temperature, we are interested in the broad temperature, or let's say like an average ZT. So for us, the material should show high ZT for a broad temperature range other than one peak temperature. And if you have these thermoelectric couples and then put them together in electrically in series and thermally in parallel, then you create these thermoelectric modules. So then the question is this: what is the ideal thermoelectric material? So this question was partially answered by Slack, basically, with this concept, what we call electron crystal phonon glass concept. For him, a good thermoelectric material should show a good electronic conductivity like found in the good crystalline materials, single crystals, for example, but at the same time, they should show poor thermal conductivity, which is typical for amorphous materials or glass. Now, it is hard to achieve this, this property because, again, these transport coefficients are interdependent. If you look at here on the left side, Seebeck coefficient and electrical conductivity, it depends on the carrier concentration, and Seebeck coefficient decreases as you increase the carrier concentration, and the conductivity, on the other hand, increases. So in the thermal conductivity, before the thermal conductivity, so this electronic part, what we call power factor here, is kind of like maximized in this case for materials which we call heavily doped semiconductors with the carrier concentration in this range. So in the thermal conductivity, so it is consisting of both the lattice and the electronic contribution, and you can see that electronic contribution again depends on the carrier concentration. So except for the lattice contribution to the thermal conductivity, all these transport coefficients are dependent on the electronic structure in a sense. So the lattice thermal conductivity is not dependent on the electronic structure, and this is further reduced by nanostructuring, for example, by microstructure engineering, by doping studies, or some materials. Luckily, they show inherently low lattice thermal conductivities, and one of these material is, or like the family of this material is called the Zintel phases. Now, traditional thermoelectric materials, as was discussed in the first talk, is actually lead telluride and silicon germanite. So these are covalent materials with electronegativity, with very small electronegativity difference here. On the other hand, the Zintel phases, they need to have both the cation and the anion. So the electropositive cation should donate the electron to the electronegative elements so that they both achieve a closed electron configuration, the stable electron configuration. So all the shells are filled in a sense with this electron transfer in this case. So in here you can see that these cations can be alkali metals, alkaline earth metals, rare earths, or even transition metals. You can just add the transition metals to the structure, and the anions are on the right side, the p block elements mostly. Okay, so what are the Zintel phases? So in the audience, maybe people are not familiar with the Zintel phases, but the the Zintel phases are basically kind of composite materials in the atomic scale. So they have this anionic structure. You can see these are all anionic structures. So this is kind of zero-dimensional, individual, independent tetrahedra. Here you can see that the corner shaped tetrahedra in one dimension. This is kind of creating slabs, the layers in the 2D, and also they can have the 3D structure. This is the anionic structure, and the structure have strong directional two-center, two electron covalent bonds. But there are also these cations, kind of like fitted inside these holes. They act like a glue, and they have soft, non-directional ionic bonds with the covalent anionic structure. So the Zintel phases, they show basically inherent lattice thermal conductivities, as you can see here. Like these are the watt per meter Kelvin, so they can go below 1 watt per meter Kelvin. And you can see that there's a trend as you increase the complexity of the crystal structure, for example, in the Zintel phases, then the lattice thermal conductivity even drops down significantly, as you can see here. This has only 6 atoms per unit cell. This has 208 atoms per unit cell. And you can see that this shows the lowest thermal conductivity. So, clatrates, they are Zintel compounds, and they are indeed inclusion compounds with the three-dimensional framework of tetrahedrally coordinated host structure. And this tetrahedrally coordinated host structure is composed of these large polyhedral cages, like formed by this pentagonal or the hexagonal rings, actually. So these polyhedra are creating this 3D framework of the host, and inside of this, the gas atoms, the electropositive gas atoms, are basically encapsulated. So you can see that there are different types of clatrate structures. I put here only 3 of them. There are more of these structures which are built by different building polyhedra, as you can see here. So these have very large unit cells actually. This one has, for example, 124 atoms per unit cell. This is type 1 clatrate, so 54 atoms per unit cell, and this is 124 atoms per unit cell. And this unit cell can even bear some vacancies in the crystal structure because of this electron transfer and the Zintel concept. So these materials can be semiconductors, as you can see here with these vacancies. This has perfectly charge balanced composition, but they can also show metallic behavior because of this extra, for example, electrons in the composition, in the structure. Okay, so here I show you let's say like the best p-type and n-type thermoelectric materials for different types of thermoelectric families, and focusing on the clatrates, you can see that as a p-type material, one of the thermoelectric material, let's say the p-type ones, are here in the pink one, and also for the n-type it is shown here. So this is kind of good thermoelectric in the p-type, so at the mid-temperature range, but this one is rather, let's say, like low to mid-temperature range. So thermoelectrics can be good, clatrate thermoelectrics can be good, both, let's say, like the low temperature or the mid-temperature applications. And there are other materials in the clatrates, they can be even functional at higher temperatures. So we were working on the different types of clatrates and then trying to put them together in different properties and see if there is a trend there for different clatrates. When I put here silicon, germanium, tin, or vice versa, or the others. So here, these are the elements building this framework structure, actually. And what we can see here is the hole mobility versus the Seebeck effective mass. So generally, the hole mobility is higher for thermoelectric materials, and for the clatrates, as you decrease the effective mass, you can see that the hole mobility basically increases. And generally, the high hole mobility is seen mostly for the tin and the germanium-based clatrates. So, good thing with the clatrates is this: the same material can show both N and P-type behavior. You can see here, for example, the red ones are silicon clatrates. They can show both P-type and N-type behavior. Or the same holds here for the germanium. It shows both p-type and n-type behavior. So the sign of the Seebeck coefficient is telling you if it is p-type, if it is positive, it is p-type, and if it is negative, it is n-type material. Why this is important? Because you are making these thermoelectric modules and you need p-type and n-type material. So if you construct the module with the same type of material, then you will have this less problem with this thermal expansion, as was discussed in the first talk again. So the clathrates being very complex, with the complex structures having high number of atoms, basically, they show this low thermal conductivity. This is kind of like phonon glass electron crystal nature of these materials. So most of them show less than 3 watt per meter Kelvin of thermal conductivity, and as you can see here, the lowest ones are the heavy one, which is actually the thin clathrates. So as you look at the lattice thermal conductivity, if you fit a line here, you can see that this total thermal conductivity, the contribution of the lattice thermal conductivity to the total thermal conductivity is around 70%. So I plotted here the weighted mobility versus the lattice thermal conductivity. The reason that I plotted in this way is this. In addition to ZT, we can also define the efficiency with the quality factor, what we call the quality factor. And this is telling you or giving you an impression about the maximum ZT which could be achieved. And this quality factor depends on the weighted mobility and the lattice thermal conductivity. Higher the weighted mobility and lower the lattice thermal conductivity, you will get the higher beta values. And you can see here, for example, the thin clathrates, they show high weighted mobility and intrinsic low lattice thermal conductivity. And then the germanium ones is kind of in between. It shows moderate weighted mobility and moderate lattice thermal conductivity. So if you look at here, the peak ZT and the temperature, you can see that at low temperatures, we see higher ZT values for the thin clathrates. At the mid-temperature range, we see better thermoelectric properties for the germanium clathrates. And at higher temperatures, actually, we see good thermoelectric performance for the silicon ones. So there are not many materials which can basically be stable up to these temperatures of like 1200 K. In this case, so we have large extent of these thermoelectric materials which could be applied in different temperature, let's say different applications requiring different temperatures, as the low temperatures, mid temperatures, or the high temperatures here. Okay, clathrates, besides the thermoelectric applications, they are known to show superconducting behavior, especially the silicon ones, as I put here, one of the type 1 clathrate, barium nickel, in the barium nickel silicon system. Now the existence of superconductivity for silicon clathrates with this sp3 framework, right, all the silicons are, let's say, tetrahedrally bonded, is kind of unusual, because this structure is dominated by strong covalent bonds, and most of these the traditional superconductors are known to show the metallic bonding, right? So now these materials, barium nickel silicon clathrates, were prepared in a argon-filled glow box, and we did high temperature annealing in these glassy carbon crucibles, or in tantalum ampules. And if required, which will be the case, as you will see, for the superconducting compositions, we used the quenching. Basically, what we did is we melted these materials in a high-frequency induction furnace, and then quenched it between the steel plates, so that we basically kind of freeze the high-temperature composition or the modification. And then, of course, we just cut the samples and do all types of transport property measurements. Now, if you look at the microstructure, these are based on the nickel content. So here we have the lowest nickel content, and here we have the highest nickel content. In the lowest one, besides the clathrate phase, which is actually shown in this gray area, we see also the silicon and also the barium silicide, for example, in the white range. So here you can see the Xrds. These are the theoretical powder patterns for the type 1 clathrate. And here, for the steel quenched materials, these are the ones actually showing the superconducting property. They are obtained after steel quenching, and they have a lot of silicon and also the barium disilicide. Of course, we should be able to get rid of them, and we did it with the sodium hydrochloric acid and sodium hydroxide treatment. And then we ended up with very nice single-phase clutterate materials. So we did also an extended phase diagram analysis, as you can see here. This is where these clutterate compositions are, and they have different, basically, neighboring phases, or the phases in which this clutterate phases is in equilibrium. So if you just look at here, if we don't have any vacancy, the nominal composition should basically be on this line, on this dotted line. But with the vacancies, we just see that there is small deviation. And all these, let's say, like empty circles or the filled squares, they are the ones, basically, the composition was found with, for example, WDS, which can give you really quantitative composition. Okay, so this is, again, the crystal structure. And in the crystal structure, we have the barium encapsulated in the cages, and nickel and silicon forming this polyhedra, and we can even have the vacancies, which results in these lone pairs, let's say three-bonded silicon in the crystal structure. Okay, so here we determined how the lattice parameter is changing, for example, for different types of clutterates, starting from barium 8, silicon 46. So this is also a clutterate with the TC of 8 Kelvin. So here there is no nickel, here there are a little bit of nickel, and here we have higher nickel content, and these are the determined nickel content. So this is barium 8, silicon 46 was obtained at high pressure, so this is not from us, from the literature. Steel quenched ones were obtained by by the low nickel content ones were obtained by steel quenching, and high nickel content ones were obtained by actually solid state annealing. And here we see the resistivity behavior to determine the TC of these materials. So for both this nickel 1.4 and 1.6, we see this transition to zero resistivity with onset temperatures of 6 or 5.5 Kelvin. So we have this broad range of transition, which might be attributed to the small homogeneity range of this steel quenched materials, basically. So the sharp decrease, basically, here you can see that there is this TC versus the nickel content, and this is for 846. These are low nickel content, and this is high nickel content. And this sharp decrease in TC with the nickel content basically is reflecting the change in the density of states near the Fermi energy level, which doesn't change quite much from 0 to 2 nickel content, but it changes dramatically from 2 to 3, so which actually affects this electron phonon coupling and then killing the superconducting behavior. Okay, so at the end of my talk, I would like to thank my supporters, let's say, supporting agencies, and also our big group at this Koç University Boron and Advanced Materials Application and Research Center, and thank you for your attention.
Thank you very much. And
Sure.
that is, these Zintel phases are very interesting for historically, but there is, in recent years, there's a number of publications in both in structure, in some numbers of structure and bonding, and in the literature in general, and also with theoretical analysis from Ángel Vegas, who finds these, he can explain a lot of the structures of inorganic solids based on this Zintel concept. He calls it the extended Zintel concept, and I don't know if you have seen it, because that could be helpful in guiding the way you direct your exploration for these type of properties. It could be very interesting.
Sure. I know about the extended Zintel concept, and like just for practical information. So Zintel concept is especially useful to find the relationship between the crystal structure and the property, because based on this charge transfer between the cation and the anion and the resulting anionic and the cationic structure, you can basically estimate what kind of for example, electronic property you would estimate, or with the number of atoms in the unit cell, you can estimate to what extent the lattice thermal conductivity could be decreased, and etc. So it is quite useful for understanding again the structure and the property relationship.
Yes, definitely. I think that's the right way of thinking. It's a much more it's a much better approximation to the reality of the crystal structure in materials than what we had before that. So I think it's a very nice. I would say it's a very nice strategy from your point of view to continue along that way. And I suggest that you check this extended model, but the one with interpretation that Angel Vegas and many other people that collaborate with him, also from the theoretical point of view. And you're right, it's what affects the electronic density and how and its distribution, which is what really gives you a lot of the properties that you're looking for. So it's really interesting. So thanks for this very nice talk, and I think then we have a small delay, but you will be a co-chair in the next session. So I think we will make a break. I am not sure we have the first speaker of the next session. Now we have another talk now, but then the second session after the break, I am not sure we have a connection with the speaker. So we will, if we don't, then I will make an announcement, or we will put a message so that we can start with the second lecture of the next session. So now we have another talk. Thank you very much again.